Greetings for the day. I am Dr. Onika Parmar and I welcome you all in the course Fundamental of Electronic Engineering, and today we are going to discuss about the channel formation in metal oxide semiconductor field effect transistor, that is MOSFET. So, today we are going to discuss about channel formation in the MOSFET. So, in this comprehensive introduction, we will have a deep discussion into the intricacies of channel formation in a N-channel MOSFET device, exploring the fundamental principles governing electron flow and how the gate to source voltage dramatically influence the creation and modulation of this conducting channel, ultimately shedding light on the role it plays in enabling the flow of electrical current within these semiconductor devices. So, these are the outline for today's class. First of all, we will discuss about the structure of N-channel enhancement mode MOSFET, followed by the basic transistor operation. Then we will discuss about ideal MOSFET current voltage characteristics for a NMOS device, and then in this it will be divided into further section. So, first we will discuss about transistor structure at VGS greater than the threshold voltage and for a small value of VDS. Further, we will discuss about the transistor structure for VGS greater than threshold voltage for a larger value of VDS, but less than the saturation value. We will discuss for the condition where the gate voltage is greater than the threshold voltage, and here in this condition the drain to source voltage will be equal to the saturation value. And lastly, we will discuss about the transistor structure when the gate voltage is greater than the threshold voltage, but the VDS has moved further than the saturation voltage. Before moving ahead in this lecture, I would like to discuss about the previous class, that is I will like to show the enhancement type and the depletion type MOSFET here. So, here you can see there are two transistors. The first one shows a depletion mode MOSFET and the second one shows enhancement mode MOSFET. So, as I have told you in the previous lecture, the depletion type MOSFET channel already exists in the device, while in the case of enhancement type MOSFET channel is not fabricated while the fabrication process. So, here we can see that beneath the gate terminal there is a yellow color element, that is the channel, which is being placed while the process of fabrication, while we can see a enhancement type MOSFET. Here there is no channel present in the device structure. The channel is formed when we apply any potential. So, basically enhancement type MOSFET is used where we want to have more control over the circuit. Now, moving ahead about the structure of the N-channel enhancement type MOSFET. So, we will now apply the concepts of an inversion layer charge in a MOS capacitor to create a transistor. So, figure 1 shows a simplified cross section of a MOS field effect transistor. The gate, oxide and p-type substrate region are the same as those of a MOS capacitor that I have explained in the previous lectures. So, this figure shows the schematic diagram of a N-channel enhancement mode MOSFET. So, here we can see this is a N-type MOSFET. So, the substrate in the N channel MOSFET is of P type. Now, we can see there is a source region and a drain region. The source and the drain regions are heavily doped. So, we can see there is written N plus. So, if N plus it is written, then means that area is heavily doped. If it would have written P plus, then it would be a P type doping, P type heavily doped. Here it is written as N plus. So, there will be a N type doping and the doping will be high. So, there is a P substrate, we have taken a P substrate, P type silicon, and then we have done the N plus doping for the formation of the source and a drain region, and above that there is a layer of silicon dioxide, and over the silicon dioxide a polysilicon material or a metal is present that forms the gate of the channel. In general, a polysilicon is used as the gate material. Now, here we can see there are various terminals for the device. So, we can find there is a source terminal, there is a drain terminal and a gate terminal followed by the substrate terminal. So, there are 4 terminals in these devices. First is source, second is gate, followed by drain and substrate. Substrate is also known as body terminal. So, do not get confused. If anyone says substrate or body, they means the same thing. Here we can see that the source and the drain are symmetrical in nature. This is a very important aspect in the MOSFET formation, that the source and drain are symmetrical. We can exchange source to drain or we can replace source to drain in any device. So, what happens? This gives a ample of space for the fabrication. Therefore, this is the one major aspect which causes high density in a small area, because this device is symmetrical. This is widely used in the process of fabrication. So, moving ahead to the discussion, there is a source and a drain terminal which have same doping and same sizing, and the space between the source and drain provides the channel length. Here the channel length is represented as L, and the T-ox represent the thickness of the oxide in this structure. W represents the gate terminal, and the W by L ratio plays a significant role in determining the drain current. In addition, we now have 2 regions called the source terminal and the drain terminal. Current in a MOSFET is the result of the flow of charges in the inversion layer, also called the channel region, adjacent to the oxide semiconductor interface. The channel length is represented as L and the channel width is represented as W, as they are defined in the figure. The channel length of a typical integrated circuit MOSFET is less than 1 micrometer, that is, it is less than 10 to the power of -6 meter, which means that MOSFETs are very small in size. The oxide thickness, which is represented as T-ox, is typically in the order of 400 angstrom or even less. Even the channel length is very less. 1 micrometer is a big value in the case of a MOSFET. So, it goes very less. In nowadays, the research is going for 5 to 6 nanometer. Figure 2 shows a more detailed cross section of a MOSFET fabricated into a integrated circuit configuration. A thick oxide called the field oxide is deposited outside the area in which the metal interconnect lines are formed. The gate material is usually heavily doped polysilicon. So, here we see a N-channel MOSFET showing the field oxide and the polysilicon gate. So, as I have told you, there is a source terminal and a drain terminal. The source and drain are connected via a metal interface. So, we can see there is a source metal and a drain metal, and two field oxides are present in the device, and the gate is formed with the polysilicon material. The gate oxide can be of silicon dioxide or some another material depending upon the application. In general cases, the gate oxide is formed of SiO2, that is silicon dioxide. Even though the actual structure of a MOSFET may be fairly complex, the simplified diagram may be used to develop the basic transistor characteristics. Despite the inherent complexity of the actual physical structure of a MOSFET, engineers and researchers often resort to employ a simplified diagram to educate and derive the fundamental transistor characteristics. This simplified representation allows us to abstract away from the intricate details, facilitating a clearer understanding of how MOSFET functions in electronic circuits. By breaking down the components, a more manageable visual can be revealed into the core principle governing the MOSFET operation. In turn, this aids in the analysis of critical parameters such as threshold voltage, drain current and gain, which are the paramount of designing and optimizing the circuit parameters. Therefore, while the true inner working of MOSFET might be a very complex, a simplified diagram serves as a valuable tool in grasping their essential behavior and enabling innovation in electronic design. So, let us move towards the basic transistor operation. With zero bias applied to the gate, the source and drain terminals are separated by the P region as shown in figure 3a. This is equivalent to two back-to-back connected diodes as shown in figure 3b. The current in this cases is essentially 0 or no current flow in this case. So, here we can see the simplified structure for a N-channel MOSFET prior the formation of an inversion layer, and the second figure shows a equivalent back-to-back connected diodes between the source and the drain when the transistor is in cut-off condition. If a large enough positive gate voltage is applied, an electron inversion layer is created at the oxide semiconductor interface, and this layer connects the N source to the N drain as shown in figure 4. A current can there be generated between the source and the drain terminals. Since a voltage must be applied to the gate to create the inversion charge, this transistor is called an enhancement mode MOSFET. Also, since the carriers in the inversion layer are electrons, this device is also called as N-channel MOSFET. it is also represented as NMOS. So, this is the cross section after the formation of an electron inversion layer. So, here we can see there is a source terminal represented as S, the drain terminal is represented as D, gate terminal is represented as G, and the body terminal which is represented as B. It is also known as substrate, and here we can see the inversion has occurred and the electrons are beneath the gate terminal. So, there is a layer of electron beneath the gate terminal. Hence, this layer is called an inversion layer. This layer of electron has formed in the P substrate area. So, the layer has inverted and the electrons are accumulated beneath the gate terminal. The source terminal supplies carriers that flows through the channel, and the drain terminal allows the carrier to drain from the channel. For the N channel MOSFET, electrons flow from source to the drain with an applied voltage to the drain to source terminal, which means the conventional current enters the drain and leaves the source. So, as I have told you, the direction of the current is opposite to the electron flow. Here, the electrons are flowing from the source to the drain terminal via the channel. Therefore, the conventional current direction will be in the opposite way. So, you will generally find the conventional current in the downward direction in the case of a N channel MOSFET. You will find that the drain current will be in the inward direction at the drain terminal. This is because the current flows from the source to drain. The electron current flows from the source to drain, and the conventional current direction is opposite to the electron flow. The magnitude of the current is a function of the amount of charge in the inversion layer, which in turn is a function of the applied gate voltage. Since the gate terminal is separated from the channel by a oxide or a insulator, so there is no gate current. This makes the device to have high input impedance because the gate terminal is separated from the semiconductor via the oxide layer. So, there is no flow in the current, providing high input impedance to the circuit, as gate terminal is the input terminal. So, the device have high input impedance because of this oxide layer. Similarly, since the channel and substrate are separated by a space charge region, there is essentially no current through the substrate. Moving forward towards the ideal MOSFET current voltage characteristics, we are going to have the discussion of a NMOS device. The PMOS is the replica of NMOS. The electrons are replaced with holes there. So, once you understand NMOS, you will understand PMOS as well. So, moving ahead towards the topic, the threshold voltage of a N channel MOSFET is denoted as VTH and is defined as the applied voltage needed to create an inversion charge in which the density is equal to the concentration of majority carriers in the semiconductor substrate. Threshold voltage is the amount of voltage we need to apply at the gate terminal to create this inversion layer. In simple terms, we can think of the threshold voltage as the gate voltage required to turn on the transistor. For the N-channel enhancement mode MOSFET, the threshold voltage is positive because a positive gate voltage is required to create the inversion charge. If the gate voltage is less than the threshold voltage, the current in the device is essentially 0. If the gate voltage is greater than the threshold voltage, a drain to source current is generated as the drain to source voltage is applied. The gate and drain voltages are measured with respect to the source. Figure 5 shows a N-channel enhancement mode MOSFET with the source and the substrate terminals connected to ground. So, here we can see the source and substrate are shorted to the ground terminal and the gate voltage is less than the threshold voltage and some amount of drain to source voltage is applied at the drain terminal. Here in the figure we can see there is a space charge region. Now let us think why this space charge region has formed. Here we can see there is a N plus source or drain and P type substrate. So, this N and P forms a diode structure as we have seen in the earlier lectures. So, when N is brought near the P, the space charge region is formed, the depletion region is formed. Now, this region penetrates more towards the P terminal. This is because the P doping is lighter than the N plus doping. So, the penetration is towards the P side. Hence, we can see two space charge region, one at the source end and second at the drain end. In this biasing configuration, where gate to source voltage is deliberately maintained at a level lower than the threshold voltage, while a relatively small drain to source voltage is applied. A few critical phenomena come in the play. First, the absence of an electron inversion layer. Second, the establishment of a reverse bias condition at the drain to substrate PN junction. Third, the resultant drain current reaching 0, a condition which assumes that any PN junction leakage current can be neglected for the purpose of this analysis. So, this figure shows the N-channel enhancement mode MOSFET with an applied gate voltage VGS greater than the threshold voltage, that is, the gate voltage is greater than VTH. Here we can see the inversion layer has formed due to the voltage at the gate terminal. When the voltage is greater than the threshold voltage, the electrons from the P region are attracted towards the gate terminal and they accumulate beneath the silicon dioxide layer. So, in this figure we see the formation of the inversion layer. In this situation, an electron inversion layer is created, and when a small drain voltage is applied, electron in the inversion layer flow from the source to the positive drain terminal. The conventional current enters the drain terminal and leaves the source terminal. Note that a positive drain voltage creates a reverse bias drain to source substrate p-n junction. So, current flows through the channel and not through a p-n junction. The drain current ID versus drain voltage characteristics for the small values of VDS are shown in figure 7. When the gate voltage is less than the threshold voltage, the drain current is 0. When VGS is greater than the threshold voltage, the channel inversion charge is formed and the drain current increases with VDS. Then, with a large gate voltage, a larger inversion charge density is created and the drain current is greater for a given value of VDS. This plot shows the ID versus VDS characteristics for a small value of VDS at 3 gate voltages. So, first condition is when VGS is less than the threshold voltage. Second, when the VGS is greater than the threshold voltage. The transistor structure at VGS greater than the threshold voltage for the small value of VDS. Figure 8 shows the basic MOS structure for the gate voltage greater than the threshold voltage and a small VDS is applied in the circuit. In the figure, the thickness of the inversion charge layer increases. This shows that the relative charge density, for which this case is essentially constant along the entire channel length. The corresponding drain current versus drain voltage curve is also shown in the figure. So, here we can see a charge inversion layer and in the curve part we can see there is a curve between ID versus VDS. So, this is the condition when the gate voltage is greater than the threshold voltage and it is for the small value of VDS is applied. Now, we will discuss about the transistor structure for gate voltage greater than the threshold voltage for the condition that the value of VDS is larger, but it is less than the saturation voltage. Saturation voltage is represented as VDS sat. In figure 9 shows a situation when VDS increases. As the drain voltage increases, the voltage drop across the oxide near the drain terminal decreases, which means that the induced inversion charge density near the drain also decreases. The incremental conductance of the channel at the drain then decreases, which causes the slope of ID versus VDS curve to decrease. This effect is shown in the VDS ID curve. So, this is the condition when the gate voltage is greater than the threshold voltage and VDS is less than VD saturation. Now, we can see there is a change in the curve as well as there is a modulation in the channel inversion layer also. Now, let us discuss about the structure when VGS is greater than the threshold voltage and drain voltage is equals to the saturation value. As VDS increases to the point when the potential difference between the VGS minus VDS across the oxide at the drain terminal is equal to the threshold voltage, the induced inversion charge density at the drain terminal is 0. This effect is shown symmetrically in figure 10. For this condition, the incremental channel conductance at the drain is 0, which means that the slope of ID versus VDS curve is 0. So, we can write that VGS minus VD sat is equals to threshold voltage and VD saturation is equals to VGS minus VTH. So, when VDS saturation is the drain to source voltage, that produces 0 inversion charge density at the drain terminal. This figure shows the VDS curve when VGS is greater than the threshold voltage and the drain terminal has the saturation value. Now, let us discuss for the transistor structure when gate voltage is greater than the threshold voltage and the drain voltage is greater than the VDS saturation. So, when VDS becomes larger than VD saturation, the point in the channel at which the inversion charge is just 0 moves towards the source terminal. In this case, electron enters the channel at the source, travels through the channel towards the drain, and then at the point where the charge goes to 0 are injected into the space charge region, where they are swept by the electric field in the drain contact. In the ideal MOSFET, the drain current is constant for VD greater than VD saturation. This region of the ID versus VD characteristics is referred as the saturation region, which is shown in figure 11. So, here we can see the channel pinch off has occurred and the device has moved towards the saturation region when the drain voltage is greater than the saturation value. This comes to the end of our lecture. In this lecture, we have discussed about the structure of the N-channel enhancement mode MOSFET. We have discussed about the transistor operation and we have discussed about the current voltage characteristics for a NMOS device. So, thank you for your patience listening. Hope to meet you in the next lecture.